Circuit breakers are used to make and break circuits under normal load conditions and to interrupt circuits under fault conditions. When a circuit breaker is called on to operate, it must operate. Regular circuit breaker maintenance helps to ensure that breakers work when they're supposed to. In this program, we're going to look at maintenance for a variety of circuit breaker interrupting mechanisms, including those for air magnetic, vacuum, oil, gas, and air blast breakers. We'll also look at maintenance for a number of breaker operating mechanisms, including solenoid, motor spring, pneumatic, and hydraulic mechanisms. Breaker maintenance typically includes a variety of electrical tests. However, the emphasis of this program is strictly maintenance. Testing won't be covered. There are many different kinds of breakers and a lot of specific maintenance tasks for each. Many of the tasks are similar from breaker to breaker. However, specific sequences or procedures can vary. So check your company procedures and policies before performing any of the maintenance shown here. In this part of the program, we're going to look at some general maintenance tasks that apply to almost all breakers. These include making routine status checks, isolating a breaker from its operating mechanism, cleaning and inspecting breaker components, and checking contact adjustments. Routine status checks can be made while a breaker is energized. The purpose is to find problems early, before major repairs are needed or before the breaker fails. The checks generally include visually inspecting the condition of the breaker and recording various indicator readings. For example, bushings are routinely checked for cracks or breaks. The breaker tank is checked for signs of deterioration, such as rust or blistered or peeling paint. A routine status check also includes looking for signs of leaks, such as oil leaking from an OCB, or listening for audible air leaks, such as air leaking from an air blast breaker. The breaker's ground wires are inspected for damage, and the hold-down bolts are checked to make sure they haven't worked loose from the jarring of numerous breaker operations. In addition, breakers typically have various indicators that should be checked and documented. One of these is the position indicator that indicates whether the breaker is open or closed. An operation counter keeps track of the number of times a breaker has operated. The counter number is recorded. Other indications that should be checked and noted can include gauge readings, such as an oil level indication, temperature indications, and pressure indications. It's important to document your observations thoroughly and accurately. Such records help to track the status and performance of a breaker and identify problems before they become serious. Routine status checks are a key step in preventing breaker failures. However, status checks by themselves aren't going to ensure that a breaker will operate when it's needed. That's why most companies also have a schedule for more thorough servicing and maintenance. This involves taking breakers out of service.
I need you to switch out.
In general, a breaker is taken out of service only after the proper clearances have been received. When a breaker is taken out of service, it's first de-energized by opening the breaker. Then it's physically isolated from the system. The breaker is tested for dead and properly grounded. Control circuits at the breaker are also de-energized. Control circuits provide power for trip coils, closing coils, heaters, and other electrical devices in the breaker control cabinet. All appropriate switches and circuits are tagged according to company policies to warn others not to operate the equipment. After a breaker has been de-energized, isolated, and grounded, its control circuits have been de-energized, and all appropriate switches and circuits have been tagged, the breaker is electrically safe to work on. However, it's not mechanically safe until it's isolated from its operating mechanism. Most operating mechanisms have some form of stored energy that can trip or close a breaker even without control power. All that's needed is for a latch to move to release the stored energy and operate the mechanism. This is true with the stored energy in the springs of a motor spring operating mechanism. The stored energy in the compressed air of a pneumatic operating mechanism and the stored energy in the accumulator of a hydraulic operating mechanism. When breakers are closed, many store energy in the form of a compressed opening spring. The stored energy is released with considerable force to open the breaker. Isolating a breaker from its operating mechanism prevents the breaker from accidentally closing or tripping while it's being worked on. The purpose is to keep the workers from being injured. The way a breaker is isolated from its operating mechanism depends on the kind of operating mechanism it has. For example, the closing springs on a motor spring mechanism are physically blocked to keep them from operating the breaker. On a hydraulic mechanism, a bleed valve is opened to bleed system pressure to zero so that the breaker cannot operate. Regardless of the mechanism involved, the breaker is isolated from the mechanism to prevent accidental injuries. Once that's done, work can proceed on the breaker. Now, the actual work that you do can vary, but the general tasks for most breakers include cleaning, inspecting for damage, and checking adjustments. Among the things that should be cleaned while the breaker is de-energized are the bushings. Dirt, greasy film, salt deposits, and other contaminants from the air can accumulate on bushings and reduce their insulating ability. The interior of a breaker is cleaned for a number of reasons. One reason, with an oil breaker for example, is to reduce the amount of oil or residue that you get on yourself as you work on the breaker. Another reason is to remove carbon, arcing residue, or moisture that may affect the ability of the breaker to extinguish an arc. As you clean the breaker, you can also inspect it. Gaskets are checked for damage or deterioration. Insulating parts are checked for cracks, warping, or other damage. The breaker is checked for missing or broken cotter pins. And nuts, bolts, washers, screws, and terminal connections are checked for looseness or damage. And all internal operating rods, links, and interrupters are checked for signs of wear or damage. The contacts are an especially important check in any breaker inspection. There should be very little wrong with the main contacts, since it's the arcing contacts that break the circuit and are subject to arcing. If main contacts are burned, pitted, or charred, they may not be separating before the arcing contacts. Damaged main contacts may need to be replaced, and the open and close sequence of the contacts may have to be checked. You can expect arcing contacts to be discolored and pitted. In general, some discoloration and pitting is not harmful, as shown here. However, if an arcing contact is severely pitted or burned, it may need to be replaced. Any problems that are found during an inspection should be corrected. Replace parts if necessary, repair damage, and tighten loose connections. Anything that could affect the proper operation of the breaker or that could cause it to fail should be taken care of while the breaker is out of service. After a breaker has been cleaned and inspected, the contact adjustments can be checked. We'll look at contact adjustments in detail later, but in general, there are 3 basic contact adjustment checks. One of these is initial contact engagement, which means that when the breaker is closing, the arcing contacts should touch at about the same time. A second contact adjustment check is for contact alignment, which means that the contacts should line up with each other as they are designed to. And a third contact adjustment check is for contact wipe, penetration, or pressure. Essentially, when the contacts are closed, they should make a good, firm connection. The measurements for contact adjustment should fall within a tolerance specified either by the manufacturer or by company standards. So, maintenance tasks that apply to most breakers include routine status checks, isolating the breaker from its operating mechanism, cleaning and inspecting breaker components, and checking contact adjustments. Another area of breaker maintenance includes cleaning, inspecting, and checking adjustments of breaker operating mechanisms. In the next part of this program, we'll look at circuit breaker operating mechanism maintenance. Internal breaker components need servicing from time to time to ensure that they will continue to extinguish arcs and make and break circuits when needed. But a breaker cannot reliably extinguish arcs unless its operating mechanism also works properly. So servicing a circuit breaker's operating mechanism is just as important as servicing its internal components. In this part of the program, we're going to look at some general maintenance that applies to most breaker operating mechanisms. Then we'll look at some specific tasks for solenoid and motor spring operating mechanisms. A word of warning is needed here. For most mechanism maintenance, the source of stored energy should be blocked or discharged to keep the breaker from closing and to prevent injuries from accidental operation. General maintenance for breaker operating mechanisms is similar to general maintenance for the breaker itself. The tasks include inspecting for damage, checking adjustments, and cleaning. A little bit of dirt might not seem like a big problem, but it can cause friction and wear that may slow the mechanism down or prevent it from working and can reduce its effective life. So it's a good practice to wipe off the links, levers, control coils, latches, rollers, and other mechanism parts. Dirt or rust can be cleaned with a solvent if necessary, and a small amount of rust inhibitor can be applied. While cleaning the mechanisms, you can also inspect them. Signs of wearing may indicate that some lubrication is needed. Parts with excessive wear should be noted for possible replacement. Check for loose nuts, bolts, and screws, and tighten any that need tightening. Also, check for loose wiring connections or wiring that's frayed, cracked, or corroded. Plungers on control coils are checked to see that they move freely. Sometimes, while cleaning and inspecting an operating mechanism, you may find signs of a problem that needs further checking. For example, puddles of hydraulic fluid may indicate a leak in a hydraulic system. The source of the leak should be located and fixed. Now, while many mechanism checks are done with the mechanism blocked to prevent closing, some checks can only be made with the breaker closed or partially closed. We'll look at a few of them. First, to close the breaker, blocking that prevents closing is removed. And in many cases, another part of the mechanism is blocked to prevent the breaker from opening. Then the mechanism can be manually cranked closed. One common operating mechanism that is usually checked with the breaker partially closed is a shock absorber, often called a dash pot. Dash pots cushion the impact of rapidly moving mechanisms, primarily when the breaker opens. With the breaker closed, the mechanism linkage is lifted off the dash pot. The dash pot is moved by hand to see if it moves freely. If it doesn't move freely, it may not properly cushion the mechanisms when the breaker opens, and the mechanisms could be damaged. A stiff or jammed dash pot should be fixed or replaced. Numerous mechanism adjustment checks are also made with the breaker closed. Two of these are latch wipe and latch clearance. Latch wipe is a measurement of how much of the surface of a latch rests against a roller or other component to hold the operating mechanisms in place. Latch wipe can be checked in different ways. Sometimes, visually checking that the latch rests against a stop is all that's needed. Another way to check latch wipe is to insert a piece of paper between the latch and the roller surface that it normally holds. Slowly crank the mechanism into position so that the roller presses against the latch. When the mechanism is released, the impression left on the paper represents the latch wipe, which is compared with manufacturer specifications. Latch clearance is the amount of clearance needed for a latch to consistently drop into a given position. To check latch clearance, start with the breaker open. Slowly close the mechanism so that the latch, such as a holding latch, drops in position to lock the mechanism in place. crank the mechanism beyond the latch position as far as it'll go. Then measure the gap between the latch and the surface it normally rests on. The gap should fall within a range specified by the manufacturer or company requirements. Some other important checks are for bell crank and operating rod adjustments. As shown in this simplified illustration of an oil breaker, a bell crank is a mechanism that changes the direction of mechanical motion, such as the motion of operating rods from horizontal to vertical motion. It also sometimes multiplies movement, such as changing a short movement into a longer movement. The bell crank is checked to make sure that it is at a given position, typically when the breaker is closed. For this particular breaker, the bell crank adjustment is checked by removing the top of the bell crank housing and measuring the spacing between a pivot pin and a given surface of the bell crank housing. Operating rod adjustments are also checked. Here are two operating rods in this simplified oil breaker illustration. The operating rods are checked to make sure that they are at a given position, typically when the breaker is closed. For this particular breaker, the operating rod adjustment is checked by inserting a special gauge, called a go-no-go gauge, in through a cap at the top of the breaker and measuring the spacing between pivot pins on the operating rods. The tolerances that are allowed for operating mechanism adjustments depend on the individual breaker and are usually specified by the manufacturer or by company policy. Any adjustments that are outside of the tolerances may cause the breaker to malfunction, and they should be corrected. Now, in addition to the general maintenance tasks of cleaning, inspecting for damage, and checking adjustments, there are specific tasks for each of the four basic kinds of breaker operating mechanisms. We'll look at the solenoid and motor spring mechanisms here, and the pneumatic and hydraulic mechanisms in the next part of this program. Solenoid operating mechanisms are fairly simple. Generally, not much maintenance is required other than cleaning, inspecting, and checking adjustments. However, the mechanism can be operated electrically to make sure that it operates properly. To operate the breaker electrically, connect the breaker to a power source and energize the source. Then operate the breaker and listen for sounds that might indicate that the mechanism is not operating freely. If there appears to be some resistance, the power source should be de-energized so that whatever is causing the mechanism to bind can be found and corrected. The same is generally true for motor spring operating mechanisms. The blocking is removed. The control circuit is energized, and the operating mechanism is electrically operated to see if it works properly. A word of advice is needed here. When you energize the control circuit of a circuit breaker and operate the breaker, be sure you observe your company's tagging procedures. Now, we've seen that general maintenance for most circuit breaker operating mechanisms includes cleaning, inspecting for damage, and checking adjustments. And for the solenoid and motor spring mechanisms, there are very few additional checks. Essentially, the mechanisms are operated electrically to make sure that they work properly. Additional checks for pneumatic and hydraulic mechanisms are a little more involved. We'll look at the specific checks for these two types of mechanisms when we continue. Maintenance for solenoid and motor spring operating mechanisms generally doesn't involve much more than the normal cleaning, inspection, and adjustment checks. However, maintenance for pneumatic and hydraulic mechanisms is more involved. Many of the tasks for a pneumatic mechanism deal with its compressed air system. The specific tasks we're going to look at include draining water from the compressed air reservoir, checking the compressor oil, filter, and belt, checking for air leaks, checking pressure switches, and determining how many times the breaker will operate on a full tank of air. Before work begins on a pneumatic operating mechanism, the stored energy of the compressed air must be blocked or discharged to prevent the mechanism from operating. For some pneumatic mechanisms, the compressed air is blocked by closing an isolation valve. Closing the valve prevents compressed air in the reservoir from flowing to the cylinder piston assembly and operating the mechanism. Some pneumatic mechanisms don't have an isolation valve. Instead, the compressor control circuit is checked to make sure it's de-energized. Here, the compressor circuit knife switch is open, so the circuit is de-energized. Then a bleed valve is open to discharge the compressed air and bleed system pressure to zero. When the valve is open, it's normal for some water to blow out with the air. Water can accumulate in the reservoir due to condensation. After air pressure is bled to zero, the valve is closed and the operating mechanism can be cleaned, inspected, and checked for adjustments. The compressor is also serviced. Routine compressor maintenance generally includes checking the oil, air filter, and belt. The oil is checked in this compressor by removing an oil fill plug. A quick look in the fill hole will tell you if the oil level is okay. If the level is near the low mark on the crankcase, oil may need to be added. If the level is lower than that, you may need to look for leaks and fix them before adding oil. The condition of the oil can also be easily checked. If the oil is dark or gummy, it should probably be replaced. The compressor air filter is inspected for dirt and is cleaned or replaced if necessary. If the compressor has a drive belt, it should be checked for signs of cracking or drying out and for proper tension. If the belt is in bad condition, it should be replaced. If the tension is off, it should be adjusted. After the compressor has been serviced, it can be energized so that it repressurizes the system. When system pressure has stabilized, the air supply system can be checked for leaks. To determine if the system is leaking, take the system pressure reading. Wait a period of time specified by the manufacturer, and then check the pressure again. Any difference in the readings for the given time period can be converted to a rate of pressure drop. If the rate of pressure drop exceeds an allowed tolerance, there may be leaks in the air system. To locate leaks, apply a soapy solution to the joints in the air supply system. The solution will bubble wherever there is a leak. You can then follow the appropriate procedures to fix the leak. If a leak isn't found using the solution, the loss of pressure may be caused by a bad check valve in the supply line from the compressor to the storage tank. The valve allows air to be pumped into the tank, but it normally prevents air from flowing back out. A bad valve may allow air to leak out of the tank into the supply line. To check the valve, loosen the nut that holds the supply line. Some trapped air may hiss out. If air continues to escape, the valve is faulty and should be replaced. Other checks on a pneumatic operating mechanism are the settings of the governor switch, the low-pressure alarm switch, and the low-pressure cutoff switch. The governor switch starts the compressor when pressure drops to a preset low value. It also stops the compressor when pressure is increased to a preset high value. To check the settings of the governor switch, slowly bleed the system pressure until the governor switch turns the compressor on. When the switch operates, note the pressure. Allow the compressor to restore pressure to the system until the switch shuts the compressor off. When the switch operates, note the pressure. If the governor switch doesn't operate at the preferred pressures, the switch setting should be adjusted, or the switch should be replaced. The low-pressure alarm switch gives a warning that system pressure is getting low. If the pressure falls too low, the breaker may not operate when needed. To check the setting of the alarm switch, de-energize the compressor so that it won't operate. Then a device such as a volt-o-meter can be connected to the switch terminals and set to the appropriate scales. Slowly bleed the system pressure until the volt-o-meter indicates that the low-pressure alarm switch has operated. When the switch operates, note the pressure and, if necessary, readjust or replace the switch. The same procedure can be followed to check the low-pressure cutoff switch. This switch prevents the operating mechanism from attempting to close when there is not enough air to complete the operation. Connect the volt-o-meter to the switch terminals. Bleed system pressure until the switch operates. Note the pressure when the switch operates and, if necessary, readjust or replace the switch. After checking the switches, put their covers back on and start the compressor to restore system pressure. When pressure is restored, the mechanism can be operated to determine how many times it will operate on a full tank of air. A warning is needed here. When a pneumatic mechanism operates, air is released through an exhaust valve or port with considerable force. For safety, keep the area around the valve or port free of loose objects and stand clear when operating the mechanism. To check the operation of the pneumatic mechanism, the compressor is de-energized and control power is restored. The breaker is electrically operated until there's not enough air pressure to complete another operation. The number of operations are counted. If the number is less than that required by the manufacturer or by company policy, the operating mechanism should be rechecked to determine and correct the cause. So, some of the specific maintenance tasks for a pneumatic mechanism can include draining water from the compressed air reservoir, checking the compressor oil, filter, and belt, checking the air system for leaks, checking the pressure switches, and determining how many times the breaker will operate on a full tank of air. Now, the last operating mechanism we're going to look at is a hydraulic mechanism. The specific tasks we're going to look at include checking accumulator precharge pressure and checking hydraulic fluid levels. Accumulator precharge pressure is the pressure of the gas in the accumulator. A certain precharge is necessary to provide enough stored energy for a number of consecutive operations. One value needed to determine precharge pressure is the ambient temperature. A thermometer can be placed in the cabinet to get a temperature reading. Then a pressure bleed valve is partially opened to slowly bleed pressurized fluid into the low-pressure reservoir and reduce system pressure to zero. The valve is only opened part way, and it is closed from time to time to keep the fluid from foaming in the low-pressure reservoir. When system pressure is at zero, the bleed valve is closed and a fluid level check is made. With pressure at zero, fluid should be visible in a sight glass near the top of the reservoir. If fluid is not visible, fluid may need to be added to the system. For an accumulator that uses a bladder to separate the gas from the fluid, another check is made. Gas in an accumulator bladder will slowly diffuse through the pores of the bladder and rise to the top of the tank. With system pressure at zero, this free gas can be discharged. A small discharge is normal. If there is a large discharge, the bladder may be damaged. It should be inspected and replaced if necessary. Now, to determine the precharge, the first step is to energize the motor so that it pumps fluid into the accumulator. System pressure will increase rapidly until it reaches the precharge pressure. Then, any additional pumping will only slowly raise the pressure. When pressure stops increasing rapidly, the motor is de-energized and the pressure is noted. The ambient temperature is also noted. Acceptable precharge pressure is usually a pressure value at a given temperature. If ambient temperature is different from the given temperature, the pressure must be adjusted to compensate for the temperature difference. The manufacturer usually provides a pressure-temperature compensation chart. Using the chart, you can determine the adjusted precharge pressure. If the adjusted precharge pressure is less than that recommended by the manufacturer or allowed by company policy, gas may need to be added to the accumulator. After the precharge pressure has been checked and gas added, if needed, the motor can be re-energized to restore system pressure to normal. With system pressure at normal, another fluid level check should be made. This time, a sight glass at the bottom of the reservoir is checked. Fluid should be visible. If it isn't, bleed the system to zero and recheck the level at the upper sight glass. Then recheck the precharge pressure. A hydraulic operating mechanism will have a governor switch, a low-pressure alarm switch, and a low-pressure cutoff switch that work much like the switches we looked at for the pneumatic mechanism. The switches are checked in much the same way, by bleeding system pressure and noting the pressures at which the switches operate. After checking the pressure switches, repressurizing the system, and making sure any blocking has been removed, you can operate the hydraulic mechanism to determine how many times it will operate on a full charge of hydraulic pressure. So, some of the specific maintenance tasks for a hydraulic mechanism can include checking accumulator pre-charge pressure and hydraulic fluid level. And, like a pneumatic mechanism, the pressure switches are checked and the breaker is electrically operated to determine how many times it will operate on a full charge of pressure. Now, up to this point, we have looked at general maintenance tasks that apply to most breaker interrupting and operating mechanisms. And we looked at maintenance tasks that apply specifically to solenoid, motor spring, pneumatic, and hydraulic operating mechanisms. In the rest of this program, we're going to go back and look at some specific types of breakers to see the kind of maintenance that is done to those particular breakers. We'll start in the next part of the program with air magnetic and vacuum breaker maintenance. Many of the maintenance tasks that are performed on circuit breakers are the same from breaker to breaker. But because different breakers have different components, there are some tasks that apply only to a given breaker. In this part of the program, we're going to look at maintenance tasks that apply specifically to air magnetic and vacuum breakers. Both air magnetic breakers and vacuum breakers are typically enclosed in protective cabinets. And both types of breakers have some common features. So some maintenance tasks are also the same. For example, inspecting and cleaning the interior of the cabinet. A general warning is needed here. Before starting work inside the cabinet, make sure that the control power circuit is de-energized. In addition, even though the breaker has been removed and the control circuit has been de-energized, the bus and line connections inside the cabinet may still be energized. Sometimes these connections are behind a protective shutter. The shutter can be opened manually so that the connections can be visually inspected. When inspecting the connections, keep a safe distance from them and follow all company safety procedures that apply. Keep all tools and hands outside the shutters and visually inspect each connection for burned, broken, or worn parts that might result in a poor breaker connection. The connections for breaker control power are also checked for loose, broken, or missing parts, chips, cracks, or corrosion. They should be checked to make sure the connections are not bent or twisted out of shape so that they align properly with the connections on the breaker. It's also a good practice to clean the interior of the cabinet. Otherwise, dust and dirt can accumulate on moving breaker parts and cause them to bind. Some maintenance tasks on the breakers themselves are also the same for both air magnetic breakers and vacuum breakers. The breaker bus and line connections are checked for freedom of movement. It's important that they can swivel to align themselves with the connections in the cabinet. Retaining springs are checked for proper tension. Tight springs help ensure tight connections. Loose connections can cause high resistance and overheating. Any springs that have lost their tension should be replaced. The connecting surfaces are checked for uneven or excessive wear that may also result in a loose connection and overheating. The control power connections are inspected for loose, broken, or missing parts, chips, cracks, or corrosion. Any parts that aren't in good shape should be replaced before the breaker is put back in service. After the general external checks are made, specific internal components can be checked. We'll start with the air magnetic breaker. The main components that are checked include the arc fins, the arc runners, the main contacts, the arcing contacts, and the puffer assemblies. To get to most of the components, the arc chute is either removed or tilted back. The arc chute is an assembly that includes the arc fins, arc runners, blowout coils, and pole pieces. With the chutes tilted back, the arc fins can be inspected. Slight erosion of the fins or discoloration is generally not a problem. However, fins that are seriously burned or broken can affect the ability of the breaker to extinguish arcs. Seriously damaged fins should be replaced. Dust or loose particles in the arc chute can also affect the ability of the breaker to extinguish an arc. Here, a worker is using a blower to clean out the arc chute. The arc runners are also inspected for serious burning, metal deposits, and splitting. They should be cleaned or replaced as needed. As with the arc fins, slight discoloration or erosion of the runners is generally not a problem. Insulating parts of the breaker are cleaned with a dry rag to remove dirt or dust. An insulating solvent may be used, if necessary, to remove grease. The puffer air tubes and nozzles are also checked for damage or obstructions and replaced or repaired if needed. Other maintenance tasks include inspecting and cleaning the contacts and checking the contact adjustments. One adjustment that is checked is initial contact engagement. This is a check to see if the arcing contacts for all three phases of a breaker touch at about the same time. For some breakers, the contacts for each phase may be in separate tanks, and initial contact engagement is often checked using a continuity device. One such device, a light-out device, is being applied here on the air magnetic breaker to show how it would be used. Leads from the light-out device are connected to each bus and line connection. On other breakers, they may be connected to the conductors at each bushing. After the light-out device is connected, the breaker is slowly closed. When the arcing contacts for a given phase touch, the light for that phase will light up. The contacts for all three phases should touch at about the same time, within a specified tolerance. If they don't, the contacts should be adjusted and rechecked. Another contact adjustment check is the gap between the main contacts. With the arcing contacts just touching, the gap between each set of main contacts should be within a specified tolerance. If it's too narrow, an arc may form across the main contacts when the arcing contacts separate. An improper gap should be adjusted. A third adjustment check is contact pressure. For this breaker, the contacts are cranked completely closed. A gauge is inserted in a slot that opens under the contacts when they are fully closed. If pressure isn't sufficient to allow space for a specified size gauge, the contacts may need to be adjusted or replaced. Finally, the operation of the puffers can be checked. First, the breaker is opened for safety reasons. Then the arc chutes are carefully put back in place. The breaker is manually closed, and clean rags are placed on top of the chutes. Care is taken to stay clear of the mechanisms, and the breaker is tripped. If the puffers are working, a short blast of air should lift the rags off the arc chutes. If no air comes through, the puffers should be checked for damage, and the arc chutes should be rechecked to make sure that there are no obstructions. The maintenance tasks for a vacuum breaker are much fewer than the tasks for an air magnetic breaker. Basically, they include cleaning the vacuum bottle and checking contact erosion. A precaution is needed here. Some vacuum bottles have a ring around the middle that may be used for testing. The ring may carry a substantial electrical charge. Before work begins on the vacuum breaker, the rings should be shorted to ground to safely discharge any charge on the ring. Then the vacuum bottles can be cleaned with a dry, lint-free rag. Checking the contacts on a vacuum breaker is different from checking the contacts on other breakers because they're sealed in vacuum bottles. Instead, an erosion indicator is provided for the contacts in each bottle. An erosion indicator includes a pointer, which is mounted on the stem of the moving contact, a fixed target on the interrupter support frame, and a narrow band on the target. To check contact erosion, the breaker is closed. For a new vacuum bottle with the breaker contacts closed, the pointer should come up to the bottom of the band on the target. As the contacts erode with numerous breaker operations, the pointer moves up into the band, indicating how much contact surface has eroded. When the pointer moves to the top of the band, the contacts have eroded as much as the manufacturer recommends, and the vacuum bottle should be replaced. So for both air magnetic and vacuum breakers, their protective cabinets are inspected and cleaned, and the breaker bus, line, and control power connections are inspected. Then, in addition to the general checks, specific checks for air magnetic breakers include inspecting the arc fins, arc runners, and contacts, and checking contact adjustments and puffer operation. The specific checks for a vacuum breaker include discharging the mid-band ring, cleaning the vacuum bottles, and checking an erosion indicator to determine the amount of contact erosion inside each bottle. Other types of breakers also require specific maintenance checks. When we continue, we'll look at some of the specific checks for oil circuit breakers. Some of the maintenance tasks that apply specifically to oil circuit breakers involve handling or checking the condition of the oil. These can include checking the dielectric strength of the oil, removing and filtering the oil, ventilating gas byproducts of the oil, and rinsing dirty oil off the breaker mechanisms. Other tasks that are specific to oil circuit breakers deal with inspecting components that are unique to OCBs, such as the interrupter grids. The oil in a circuit breaker insulates the breaker's arc interrupting mechanisms and helps to extinguish arcs by inhibiting the flow of current across open contacts. But over time, the dielectric strength of the oil, its ability to inhibit current flow, decreases due to moisture, carbon from arcing, and other contaminants. So the dielectric strength of the oil is checked periodically. To test the oil, a sample is drawn through a sampling valve at the bottom of the breaker. Several gallons are drawn off to purge the pipe and make sure the sample is from inside the breaker. If water comes out when the valve is opened, it indicates that there is a leak in the breaker that is allowing moisture into the tank. The dielectric strength of the oil will probably be very low. Metal or wood particles in the oil are a sign of internal damage, something to keep in mind when you go inside the breaker to inspect the internal components. The instrument used for testing the dielectric strength of oil is fairly standard, but there can be some variations, so you'll need to become familiar with your company's specific test equipment. Typically, the test instrument has a cup that holds 2 electrodes. A gap is set between the electrodes according to the manufacturer's specifications. The cup is rinsed with oil to remove any contaminants that may have settled in it since the last time it was used. Then the cup is filled with oil from the sample taken from the circuit breaker. The test set is switched on and a dial is turned to apply voltage to the electrodes, which are submerged in the oil. A meter in the test set indicates the increasing voltage. When the oil can no longer inhibit current flow, it becomes a conductor, and current jumps the gap from one electrode to the other. This is called breakdown. When breakdown occurs, the voltage meter needle drops to 0. The highest voltage that was applied just before breakdown is the breakdown voltage. Breakdown voltage is an indicator of the dielectric strength of the oil. Typically, the test is repeated 2 more times with fresh samples of oil from the breaker. The 3 breakdown voltages are averaged and documented. If the breakdown voltage does not meet minimum manufacturer or company values, the oil may need to be cleaned or replaced. This is typically done when the breaker is taken out of service for maintenance. After the breaker has been properly de-energized, isolated, and grounded, the oil is pumped out of the breaker and into a storage tank. The pump typically includes a filtering system that removes moisture, carbon, and other impurities from the oil. The pump and storage tank are grounded to dissipate any static that may be generated when the oil is pumped from the breaker. Vents in the breaker are checked for obstructions that may prevent air from entering the breaker as the oil is pumped out. A hose is connected from the pump to a drain valve at the base of the breaker, and the valve is opened. Finally, the pump is turned on and the oil is pumped out of the breaker tank, through the filters, and into the storage tank. After all the oil is pumped out, the breaker inspection door can be opened. Combustible gas may be present inside the tank due to arcing in the oil. Care should be taken to avoid igniting any gas that may be present. Allowing the breaker to air out or ventilating it with a fan helps to remove gas and also ensures that there is enough air to breathe when working inside the tank. The internal breaker mechanisms may be coated with dirty oil and carbon, so they are usually rinsed off with clean oil by reversing the direction of oil flow through the pump and spraying the inside of the breaker. Then the internal components can be wiped off with a clean, lint-free rag to remove any dirt that didn't rinse off. Solvents are generally not used because they attract moisture as they evaporate, and moisture affects the dielectric strength of the oil and insulating parts. Other general breaker checks that are made include inspecting the mechanisms for wear or damage. A task that applies specifically to oil breakers is inspecting the interrupter grids. To allow a thorough inspection of the grids, they are typically removed from the breaker. Then the grids are inspected for signs of heat damage or erosion, especially in the areas that surround the arcing contacts. If damage is evident, the interrupter grid may need to be replaced. Before the grids are reinstalled, the contacts are inspected for signs of wear or damage. It may be necessary to remove the interrupters and disassemble them in order to thoroughly inspect and clean the contacts. After the contacts have been inspected and cleaned, the interrupter will be reassembled and reinstalled in the breaker tank. However, before the arcing grids are reinstalled, the contacts are checked for initial contact engagement and alignment. Contact penetration is also checked. Penetration is a measurement of how much of the moving contact makes a good, firm connection with the stationary contact. When all the checks are completed, the arcing grids and any other parts that had been removed are reinstalled. The breaker is closed and refilled with oil. New filters are put in the filter press, and the oil is filtered a second time when it is pumped back into the breaker tank. After the oil is back in the breaker, a sample is taken and its dielectric strength is rechecked. Finally, the breaker is operated electrically to ensure that it works properly. So, aside from the usual breaker maintenance, an oil breaker may have its oil tested for dielectric strength both before and after opening the breaker. The oil is filtered when it is pumped out of the breaker tank and when it is pumped back in. Precautions are taken to avoid igniting any combustible gas that may be present and to ensure that there is enough air to breathe inside the tank. And the interrupter grids are inspected for heat damage and erosion. Two other types of breakers we have yet to look at are gas blast breakers and air blast breakers. We'll look at some specific maintenance tasks for each of these types of breakers when we continue. Gas blast and air blast breakers have many of the same components that are present in pneumatic operating mechanisms. These include a compressor, a high-pressure storage tank, pressure gauges, and pressure switches. As a result, many of the maintenance tasks will also be the same, so we won't repeat them here. Instead, we'll look at tasks that are unique to each breaker. For a gas blast breaker, some of these specific tasks include evacuating the gas from the breaker, checking for leaks inside the breaker, servicing filters, and taking a gas sample for testing. Before the components inside a gas blast breaker can be serviced, the gas must be removed. Here, a gas servicing trailer is used to remove the gas. To remove the gas from the breaker, a hose is connected from the trailer to a gas service connection in the gas control housing. An inlet valve is opened at the trailer, and a vacuum pump is operated to remove the air from the hose and the gas storage tank in the trailer. The pump is allowed to run until a predetermined vacuum is obtained. Then the vacuum pump is turned off. Next, a valve is opened at the breaker to allow gas in the high-pressure system to flow to the low-pressure system and equalize the pressures. When the pressures have equalized in the breaker, a main tank cutoff valve is opened to allow the gas to flow from the breaker to the storage tank until pressure between the breaker and the tank equalizes. Then a compressor is started at the trailer to pump the gas out of the breaker. A refrigeration unit is also turned on to keep the gas from heating and expanding as it's transferred into the storage tank. The compressor is allowed to run until all the gas has been evacuated from the breaker. Then the vacuum pump is restarted to draw a vacuum in the breaker, ensuring that all the gas is removed. After the proper vacuum is drawn, the main tank cutoff valve is closed. Then the inlet valve at the trailer is closed, and the vacuum pump, compressor, and refrigeration unit are turned off. The hose is removed from the gas service connection, and the main tank cutoff valve is opened to allow air into the breaker. Then the inspection doors are unbolted and opened at each end of the breaker. A little caution should be taken when opening the doors. SF6 gas in its pure form is colorless, odorless, tasteless, and non-toxic. However, when arcing occurs in SF6 gas, a toxic metallic powder byproduct is formed. Gas containing this powder will have a pungent odor and is irritating to the lungs and eyes. If odor and irritation are noticeable when the breaker is opened, leave the area until it can be ventilated. Until the breaker is ventilated and cleaned, a mask should be worn so that you don't inhale the toxic powder. Protective gloves and clothing should also be worn to prevent skin irritation. After the breaker has been ventilated, the powder should be cleaned out. Besides being toxic, the powder absorbs moisture when exposed to air. Moisture reduces the dielectric strength of SF6 gas and can affect the ability of the breaker to extinguish arcs. When the powder has been thoroughly cleaned out, all rags and protective clothing are disposed of according to company policy. Then the breaker can be inspected and serviced. These tasks may be more convenient with the mechanisms racked out of the tank, although it's not always necessary. The general inspection, servicing, and adjustment checks are similar to those done for most other breakers. However, contact alignment is checked a little differently. For this breaker, with the contacts partially closed, a special gauge is placed inside the stationary contact fingers and around the moving contact. If the gauge doesn't fit comfortably, if there is interference from any of the fingers, the alignment may need to be adjusted. After all the required checks are made with the breaker racked out, any parts that have been removed are reinstalled, and the mechanism is racked back into the tank, and all operating rods and gas system tubing are reconnected. Then the high-pressure gas system inside the breaker is checked for leaks. To perform this task, pressurize the high-pressure system by connecting a nitrogen gas cylinder to the high-pressure line in the gas control housing. Then apply a soap solution to various joints of the high-pressure system inside the tank. If leaks are present, leaking gas will cause the solution to bubble. Here there's no bubbling, so the joint is tight. After all the maintenance is completed, the breaker is closed up. Before gas is pumped back into the breaker, filters that remove moisture from the gas are serviced. The filters contain a desiccant, which is a granular material that absorbs moisture. The old desiccant is removed so that fresh desiccant can be put in its place. The filter also contains filter pads that prevent desiccant dust from entering the breaker. The pads are cleaned and put back in the filter. To refill the breaker with gas, pump the air out of the breaker, drawing a vacuum. Then the appropriate valves are opened and the breaker is filled with gas. In most cases, after the breaker is refilled with gas, a gas sample is taken to be tested later for moisture content. So some of the maintenance tasks that are unique to gas blast breakers include evacuating the gas, checking the high pressure system for leaks, servicing the filter, and taking a gas sample. Now the last breaker we're going to look at is the air blast breaker. Some checks that are unique to air blast breakers include measuring the space between the arcing rings and stationary contacts, checking the space between the arcing rings and arcing probes, and checking air consumption. To get inside the breaker heads, an isolation valve is closed to prevent air from flowing to the heads, and a drain valve is opened to release the pressurized air in the heads. After the pressure is bled to zero, the inspection door on each head can be opened. The internal components are cleaned and inspected, and various adjustments are checked. For this type of breaker, the space between each arcing ring and arcing probe is checked. Here, a go-no-go gauge is used. The space between the ring and the probe should be such that one end of the gauge just barely fits between them, while the other end of the gauge should be just a little too large to fit between them. The space between each arcing ring and stationary contact is also checked. Here the check is made using an L-shaped gauge. If the spacing is not within an acceptable tolerance, the contact may need to be adjusted. Then, as with other breakers, the contacts are partially closed to check initial contact engagement and alignment. Then the contacts are closed the rest of the way to check contact wipe. After the interrupter maintenance is done, the heads are closed back up, and system pressure is restored to normal. After the pressure is restored, the breaker is closed. Air pressure is allowed to return to normal again. Then the pressure regulator is de-energized so that breaker air consumption can be checked. Air consumption is the amount of air that is used to trip the breaker and extinguish arcs. To check air consumption, note the head pressure, then trip the breaker. Then check the head pressure again. The difference between the two pressures represents how much air was consumed to trip the breaker. If too much or too little air is used, the breaker isn't working properly. The cause should be located and corrected before returning the breaker to service. So, maintenance tasks that apply specifically to air blast breakers include checking the space between the arcing rings and stationary contacts, checking the space between the arcing rings and arcing probes, and checking air consumption. Now, in this program, we looked at general maintenance tasks that apply to most breakers and breaker operating mechanisms. We looked at some specific checks for solenoid, motor spring, pneumatic, and hydraulic operating mechanisms. And we looked at specific checks for air magnetic, vacuum, oil, gas blast, and air blast breakers. As you gain experience with the breakers in your system, you'll find that no two breakers are exactly the same. Each has its own particular problems. But by learning the basics here, you'll be better prepared for the specific challenges in the field.